To get more insight on what the eigenvalues and eigenvectors mean, let's suppose all nodes in G have degree D, and suppose that G is connected. And this is also what we call a D-regular graph. So in this case, what are some eigenvalues and eigenvectors of G? Or in other words, if A times X equals to lambda times X, what is lambda and what is X? Let's try to set X to a vector of all ones. And we can see that in this case, A times X is actually equal to a vector of all these. This is because all the nodes in the graph, they have the same degree D. And by definition, this is also equal to lambda times X. And since X is just a vector of all ones, then we can see that this lambda here is actually equal to D. And here we actually found the eigenpair of the graph D, and the eigenpair has the eigenvector, which is a vector of all ones, and the eigenvalue is equal to D. So what does this mean? Intuitively, this means that this graph, it actually forms a single and large community. Now let's look at another example where G is not connected, but G has two components, and each of its component is D-regular. So basically, each of its component, every node in the component has degree D. And in this case, what are some eigenvectors? Suppose that we put all ones on all ones for all the nodes in group D and put all zeros for all the nodes in group B. What will happen? For example, let's say that one of the nodes is in group A, then we will set this corresponding element of this node in X to 1. And if for example, the last node in this graph, for example, here is in group B, and we'll set the corresponding element in X to 0. And then in this case, we can calculate what is A times X, right? And interestingly, A times X is similar to the previous case, is the concatenation of two vectors. One of the vectors is a vector of all these, and the other vector is a vector of all zeros. And what if we do the opposite? What if we put all ones on B and put all zeros on A? And in this case, the X would be just 0, 0, 0, 1, 1, 1. And then A times X would be a concatenation of two vectors. And the first vector will be a vector of all zeros. And the second vector will be a vector of all these. But in both cases, you can see that the corresponding eigenvalue, lambda, they are both equal to D. So what does this mean? Again, intuitively, this means that, and you can actually prove that in this case, this lambda D is actually it's both the first and the largest eigenvalue and the second largest eigenvalue. So we can say that this lambda n is actually equal to lambda n minus 1. And lambda n is the largest eigenvalue, and lambda n minus 1 is the second largest eigenvalue. And lambda n here corresponds to one group or one community of graph G, and lambda n minus 1 corresponds to another group or community of this graph G. Now, more interestingly, if this graph is connected, so it has only one connected component, but it's sparsely connected. Basically, it says that it only has a very small number of edges between group A and group B. What will happen? Still, in this case, the largest eigenvalue and the second largest eigenvalue, they will be still very similar. And again, this lambda n, the largest eigenvalue, will correspond to the largest group in this graph, and lambda m minus 1 will correspond to the second largest root in this graph. So next, let's take a step back and talk about matrix representations of graph. Note that previously we have already discussed the definition of adjacency matrix A, where it's a n by n matrix, and Aij, which is the element in the ith row and the jth column, and this Aij equals to 1 if there's an edge between node I and node j, and it's equal to 0 if there isn't an edge between node I and node j. So basically, for this graph, the corresponding adjacent matrix would look like this. And here are some important properties of adjacency matrices. And the first one would be that it's a symmetric matrix, because we're focusing on undirected graph here. And the second property is that the eigenvectors of this adjacency matrix are real. So all their elements are real numbers, and these eigenvectors, they are orthogonal to each other. And let's define a degree matrix D, and this is just a simple n by n diagonal matrix where dii, which is the ith element in the diagonal. Now, so dii is equal to the degree of node I here. For example, in this graph, the corresponding degree matrix would be this diagonal matrix. So we can see that the degree of node 1 is 3. Correspondingly, this element in the matrix is 3. So with the definition of adjacency matrix and degree matrix, we can finally define the Laplacian matrix. So Laplacian matrix is a n by n symmetric matrix, and it's simply the difference between the degree matrix and the adjacency matrix. So it's equal to D minus A. So, and interestingly, there is a trivial eigenpair for any Laplacian matrix. To see this, let's set the x to a vector of all ones. And if we compute the Laplacian matrix L times x, we can see that it will result in a vector of all zeros. Why is this? This is because if you look at this matrix, if you sum up each row, they're actually equal to 1, right? And if you sum each columns up, they also equal to 1. And since L times x is equal to 0, the corresponding eigenvalue lambda is also 0. Therefore, we find a eigenpair where the eigenvector is a vector of all ones, and the eigenvalue is 0. Again, here are some important properties of a Laplacian matrix. The first one is the eigenvalues are always non-negative real numbers. So we can see that this lambda, which is 0 here, is actually the smallest eigenvalue for any Laplacian matrix. And the second property is that the eigenvectors are real and orthogonal, and this is actually similar to the adjacency matrix property.